I want you to do one quick activity that help us understand the rest of the theories. So, you probably don't see this link, so I'm going to click on it. So there is a 80-second video that I recorded here in Pasadena. I went to take a walk at Rose Bowl. There, I basically started recording a video that I thought is useful for today's lecture. Any person that enters the scene, you think of them as an arrival, as a person who enters the system. Okay, so I'm going to use this as stopwatch, and I'm going to only look at the bytes that I see. This is what you will be doing for any system. So that's the, wait. So I'm gonna start, and every byte that I see, I click on the on the flag. So start, first one, next one, next one, another one, another one, another one. I think it's the last one. All right. So you see that I did it only for bikes. You could have done it for basically people or all together or just cars. Here you see that these are inter-arrival times. Okay. So the time between arrivals. This is what we will be working with. And when I talk about the distribution, I'm talking about these guys. Okay. So lambda is 1 over the average of these. And also you can see that here I have 1, 2, 3, 4, 5, 6 arrivals, right? I saw 6 bytes in how many minutes? 1.33 minutes. So 6 over 1.33, whatever that value is, 6 divided by 1.33. That's 4.5. 4.5 bytes per minute. So that is my lambda. Lambda for bytes. Okay. So lambda is always the number of arrivals. So this is an estimate of how many bytes I'm going to see in the next minute or every minute. But does that mean that I'll exactly see 4.5 bytes? No. It means if I look at chunks of 1 minute of this video every day, I do this thing or I do it for 1,000 minutes. On the average, this is how many bytes I'm going to see in every minute. And that's my lambda. And this value that I get, 1 over that, which is 1 over 4.5, that's the average inter-arrival time. All right. So this helps us understand the next concepts that I'm going to explain. Okay, 5 over 1.33 is going to be my lambda for people, which is 4.9 something, I guess. And if I look at all of them together, I see a larger value. All right, now I'm trying to model the arrival process. So any system that you want to study, that's how you basically collect the raw data. Everything starts from here. So here at some point we saw that 2 bikes or 3 bikes arrived very closely, like they followed each other. They were like a family or something. We can't say 3 bikes entered at the same time. Here on my stopwatch, I see that they're very close, right? 47, 49, 52, but there is a still distance between them. So inter-arrival between these is 3 seconds, 1 second, 4 seconds, and then it's 39 seconds between the third bike and fourth bike, right? 39 seconds. And then the other two are also very close. So that's why we say at most one arrival at a given instance of time. Okay, even if the distance between 2 bikes were like 0.5 seconds, we would still say they're separate. They're not entering at the exact same time. So that's one important assumption. Now let's say I equals 1, 2, 3 arrivals. So bike 1, second bike, third bike, so forth. And T sub I is arrival time of customer I. So in this stopwatch, this is TI, right? Arrival time of the first one, arrival time of the second one, arrival time of the third one, and so forth. And so these are TIs. But what are these? We call those capital TI, which is TI plus 1 minus TI. For example, arrival time of the fourth bike minus the arrival time of the third bike. We call that the random variable. So that thing, that value here, so capital T is this value, inter-arrival time, right? And as you can see, this value keeps changing, right? So it's a variable. So if I ask you, we didn't see the rest of the video. If I ask you, what is the next? So this is T6, capital T. If I ask you, what is T7, what would you say? You would say, I don't know, but it's a random value. You really don't know when the next bike is gonna arrive. So that's random. It's totally random. It could be next second. It could be, it could take 1 minute. It could take 1 hour. We don't know, right? But what we can do is to assign a probability to all the values that it can take. For example, the probability that it arrives in the next 10 seconds is larger than the probability that it arrives after 1 hour, the next bike, right? So because of that, we define a distribution that tells us, that gives us an idea of how likely it is for the next arrival, for the time of the next arrival, inter-arrival time of the next arrival or next bike. So let's call that TI, let's call that a random variable, and we call it A. And these inter-arrival times are independent. As you can see, this does not depend on the previous value, and this value does not depend on the, for example, this third bike was not asking this second guy, hey, let's live together or something. They are all independent. And the value, these values are continuous. What does it mean? It means you can get 39, 39.25, 4.92. You can get any value on the spectrum. It's a continuous value. It's not just integers, for example. So hopefully by now you know what this inter-arrival time means. Now, let's define a function at that gives us the probability of this random variable a being a certain value, which is this t. And this t is different from this one, because this was the exact t that they arrive at. For example, a of 5 means the probability that it takes 5 minutes for the next arrival to arrive, for the next bike to arrive. Let me write probability that it takes around 5 minutes for next bike to arrive. So we call, so this probability that A arrives at time t is basically the probability that, because this is a continuous value, we can't say exactly 5 minutes. We say between 5 minutes and 5 minutes plus 1 second. So 5 plus 1 second. And that way, we can calculate the probability by saying that. Why do we write that? Because if this is A, T, right, and this is T, because this is a continuous variable, if I ask you what's the probability of arriving at time t, you have to get the area under the curve, and area under the curve for this exact time is 0. So I have to stretch this a little bit and calculate this area. And this area is, the height of this area is A of t, and the width of it is t plus delta t. So the width is just 1 second. This area under the curve is the probability that the next bike arrives in 5 minutes. Not in 5 minutes, at 5 minutes from now. So probability that the next bike, arrival time of the next bike is less than c, for example, less than 3 minutes. It means the next bike arrives anytime between now and 3 minutes, anytime. That is integration of 0 to 3, or c, at dt. And the probability that it arrives after 3 minutes, or after time c, whatever that c is c to infinity at dt. And if we do this integration, we're going to get, I'm going to write the simplified formula for, which is called the CDF, cumulative distribution. So if this is C, this whole area, this entire area is probability that T is less than C. A is less than C, sorry. What is A? A is the interarrival time of the next bike. The time until I see the next bike from the last bike that I have seen. And that is 1 minus e to the power of minus lambda t. If this distribution is exponential, which we assume that it is. So this is for exponential. And this is e minus lambda t. So exponential distribution. Exponential distribution models natural processes such as arrival of bikes, people, cars, and many of the natural processes follow this exponential distribution, but the lambda difference is different for different events or different processes. You could have any distribution for arrival process. So for example, if this is my distribution, This is a uniform distribution. What does that mean? Let's say this is 100. This is 0. This distribution uniform means that inter-arrival time, which is a random variable, can be anything between 0 and 100 minutes, and it's equally likely that any of these, for example, the next bike comes in 50 minutes, that's equally likely to next bike coming in 10 seconds. And that is equally likely to next bike coming in 60 minutes. These are all equal. But this distribution tells us that the probability that it comes in the next, for example, 5 minutes is larger than the probability that it comes between 60 and 65 minutes, because this area is larger. If the distribution is, for example, like this, it's normal, and this is 10 T80. That means most of the inter-arrival times are around 10 minutes. And it's very, very unlikely that you have to wait for example, more than 30 minutes. The probability that you wait for more than 30 minutes is very unlikely. So why do you think, from the bike or from the short video that we saw, why do you think this is not a good distribution for what we saw? This normal distribution. This distribution is telling us that the probability that the next arrival is between 0 and, for example, 2 minutes is very small. It says inter-arrival times are mostly around 10 minutes, right? This is good for example, manufacturing process, a service process that processes the food or the product approximately all of them around 10 minutes. But not for a process like the video that we saw. Why? Because in the video we could see that sometimes the inter-arrival between the bikes, for example, those 3 bikes, they were so close, and it's actually very likely that they come one after the other. So this is not a good model for our natural process, arrival process. This is also not likely, because here it says this is not also a very good model, because it says probability that you arrive, for example, in this time frame, it takes, for example, between 90 and 100 minutes for the next arrival, is equally likely as this. That's a uniform process, and that's not really a good model for what we saw. But Poisson process is a very good model, very good approximate for the for natural processes, such as the one we saw in the video, when things are totally random. Okay. This is the probability that if at any point in time, you start watching to that video, and you haven't seen that video any let's say I record another video tomorrow, right? And I play it, you see one bike passing, and I pause it right there, and I ask you, what is the probability that you have to wait 6 more minutes to see the next bike? And that is that A of 6 is that probability. The probability that you see the next bike in 6 minutes, and you have no idea, but you have collected data and you think that Poisson is a good model. So it's probably very, very a small probability. Let's put that, let's change that to 0.08. This is just an example, but this is what it means, and I want to make sure that you know what it means. What is this? P of A less than 6. It means I played a video, I'd record the video tomorrow, I play it, and the first spike I see, I pause it and I ask you, what is the probability that the next spike in the video comes under 6 minutes? That includes 1 second, 10 seconds, 1 minute, 4 minutes, 5 minutes, 5 minutes, 40 seconds, all of those. Then you would say it's actually very likely, maybe 90%, right? So this exponential distribution here does that for you. Make you, this helps you give me very exact values. For example, this is 6. All you have to do here to get this area, you write 1 minus e to the power of minus lambda t, and t is 6 here. Lambda times 6. 1 minus e to the power of minus, we already calculated lambda. It's 4.5. So you just write 4.5 times 6, right? That gives me the probability. A of 6 is P of A being exactly 6.